Good morning, everyone. Today we will continue studying the topic of unsaturated compounds. As we have mentioned, unsaturated compounds can be classified into alkenes, alkynes, and alkadienes. As we have mentioned, alkenes are doubly bonded compounds. They are compounds that contain double bonds. Alkynes are compounds that contain triple bond. Conjugated dienes are compounds that have a conjugation between single and double bond. They have a 1,3-diene compounds. They are 1,3-diene compounds. Today we shall deal with the conjugated diene compounds. This is the main topic that we will be discussing in this video. Conjugated dienes are compounds, as I've mentioned, that have a conjugation where they have two double bonds separated by a single bond, an alternation of double, single, double. These are very stable compounds due to this conjugation. They are stable compounds. They are named as if you're just naming a regular functional group compound, where you give you look first for the longest chain containing the functional group. Suppose that this is your chain. You number so as to give the functional groups the least possible numbering. So this is a butane. You remove the ane, and this is a doubly bonded compound. So this is a butene, and it does not contain one double bond. It contains two. So this is a butadiene compound. The positions of the double bonds are the 1 and the 3 carbons. So this is how you name them. Suppose you have a longer chain. Again, this is a conjugated diene. Your number of carbons are 1, 2, 3, 4, 5, and 6. So this is a hexane. And then you remove the ane and you say that this is the hexadiene. Your numbers are 1, 2, 3, 4, 5, 6. So your double bonds were at carbon 2 and carbon 4. So this is the 2,4-hexadiene, and so on. Okay. Types of dienes are not just the conjugated dienes. You can have several types of dienes, where you have what we say cumulative dienes, where you have the two double bonds on the same carbon. This is called cumulative or cumulated dienes. You have the separated or the isolated dienes, where they are totally unrelated to each other. And you have the conjugated diene, where they are separated by a single bond. As I've mentioned, we are dealing with the conjugated dienes, and we have just studied how to nomenclate them. This is the organized slides indicating what we have just explained. As I've mentioned, dienes can be classified into cumulative, isolated, or conjugated. Cumulative, where the same carbon carries both double bonds. Isolated, where they are not related to each other. And conjugated dienes, where they are separated by a single bond. As we have mentioned, in nomenclating these compounds, you choose the chain and then you number from the side, giving the double bonds the least possible numbering. If you are dealing with their EUPAC nomenclature, you will have to mention their geometrical isomerism. Compound, if we discuss it on such a compound, you will have this double bond. As you have studied in stereochemistry, you determine or you specify the double bond, and then you start checking the bulky groups attached to the double bond. For example, regarding this carbon, the bulky group is the 1 carbon, so this is up. And then regarding the 3 carbon, the bulky group is the 4, so this is down. Here you have the two groups on different sides from the double bond. This is the double bond. One group is above it and the other group is below it. So this is the trans or the E. So this is the 2E. Now let's check the other double bond. Again, you will have to specify first the double bond. So this is your double bond. Let's check the bulky group on the 4. The bulky group on the 4 is up. And let's look for the bulky group on the 5. It's down. So they are both on two different sides from the double bond. This is the double bond, one above and one below. So again, this is the cis. Let's check a compound like this one. So here's your double bond. The bulky group on the 2 is down, and the bulky group on the 3 is down. So this is a Z or a cis. So this is how you nomenclate these compounds. Now, when we start discussing their mode of synthesis, or the how to synthesize these compounds, they can be synthesized in exactly the same way as you synthesize alkenes. When you synthesize alkenes, you get two carbons, you put on one an OH and on the other a hydrogen, and you remove a molecule of water using sulfuric acid to produce the double bond. Or you can have the same but halogen instead of the hydrogen, and in this case you use the base, which is alcoholic potassium hydroxide, to remove the acid, which is the hydrogen halide, to produce the double bond. Now what you need to do is to put two more carbons on this structure, having the same groups that you have just placed. How do we do this? So now you have a 4-carbon compound. You place an OH on both terminus, on the peripheral carbons of the compound, and you use phosphoric acid. You use the phosphoric acid, which is stronger than the sulfuric acid in removing water, to remove two molecules of water and produce two double bonds. So now you have the first double bond and then the second double bond. Or you can again place halogens instead of the OHs, and again hydrogen to remove the hydrogen halide and produce the conjugated diene using either alcoholic potassium hydroxide or sodamide, whichever base you prefer. Okay, the most important thing is that you have to have the halogen or the OH on the terminal carbons of the 4 carbons that you're going to use for the preparation of the diene. If you place one of the carbons or both carbons not on the terminal inside the structure, the first base molecule will remove a hydrogen halide molecule, and then the second will remove another hydrogen halide molecule, and you will not end up with a conjugated diene. In case if you place both non-terminal, what you will end up with is the triply bonded compound. So you need to put them on the periphery. You need to have them far away from each other. You need 4 carbons. You will put them on the first of the four carbons and the last of the 4 carbon. Carbon 1 and carbon 4. You have to place the groups that you will remove, whether the OH or the halogen, on the terminal carbons of the 4 carbons that you're going to use to produce the alkadiene. If you are removing a molecule of water, you will use phosphoric acid. If you are removing a hydrogen halide molecule, you will use a base, which is the alcoholic potassium hydroxide or the sodamide. This is how it is drawn in an organized manner. You have the conjugated diene, you place the OHs on the terminal carbons, and you use the phosphoric acid in high temperature. You do not need to memorize the temperature. You end up with the conjugated diene, or you can have a halogen here instead of the OH, and in this case you will use alcoholic potassium hydroxide, and again you will get the same product. These compounds have different conformers, and you have to remember very well the difference between conformers and configurations. Conformation is when you have uh, um, free rotation around a single or a sigma bond, while configuration is when you do not have free rotation, when you have restricted rotation around double bonds or cycloalkanes. So now, if we look at these compounds, you have both configurations and conformations. Configurations when you're discussing the groups around the double bond here and around the double bond there. However, they have conformations when you are discussing the orientation around this single bond. If you have both double bonds on the same side of the single bond, this is the cis form. If you have each double bond on a different side of the single bond, you have here the single bond, one double bond is below and the other double bond is above. This is the trans conformation. However, you cannot use the word cis and trans for conformations. It's only used for configurations, which cannot be interconverted to each other by just simple rotation. While conformations can be interconverted, as you can see, you can just rotate, you can just bring this bond up. This way you will have the other conformer. They can be converted into each other just by simple rotation around the single bond. So you cannot just say cis and trans. This will be totally wrong and totally confusing. So instead you add an S at the beginning, a small s. It's an S cis or an S trans. This small s gives an indication that these two compounds or these two conformers, they can be interconverted to each other through rotation around single bond. The S states, means that you are rotating around a single bond and that this is a conformation and not a configuration. Now, when we move to the reactions, they have the regular known reaction of any unsaturated compound, which is the addition reaction. They can have two types of addition reactions. We have irregular addition reactions, and we have the cyclization using the addition reaction, which is the Diels-Alder reaction. Regarding the regular addition reaction, you have a compound that contains two double bonds. If you add a hydrogen halide to this compound, what do you expect? You expect the hydrogen halide molecule to add to one of the two double bonds. So you should expect to get this product, a hydrogen here and a halogen here, and the double bond is here. And if you add another molecule, you should get another addition. However, this is not the only product you get. You get a double product. You get hydrogen here, halogen there, and the double bond moves to the middle bond. How is that done? If you try to figure out what happened is that you added the hydrogen to this carbon, you moved this double bond to this carbon, and then you opened this double bond and you placed the halogen here. So what you did in the first product is the 1,2 addition, where you added both your atoms of the molecule to the carbon number 1 and carbon number 2. While in the second product, you have performed a 1,4 addition, where you have added your products to you added your atoms to carbon number 1 and carbon number 4. How is that done? It's done because these compounds can form resonance when they carry a charge. So if you have the hydrogen halide, the bond breaks to attack the hydrogen. So now you have your hydrogen has been attached to this carbon, and you have a positive charge on the second carbon. When you broke this bond, you took the electrons to this carbon to use it to attack the hydrogen. So this way, this carbon was deprived from its electrons, and accordingly, it's carrying a positive charge. As you know very well, when you have a positive charge on this carbon followed by a double bond, one bond away, a resonance process can take place to stabilize the compound, where the double bond moves to this carbon and the positive charge moves to that carbon. As we always say, it's as if you have moved the charge from carbon 1 to carbon 3 and the double bond moves from 2 to 1. Resonance occurs when you have 3 carbons, 2 of which are attached by a single bond and the other 2 are attached by a double bond, and you have a charge on the carbon number 1. You move the charge from 1 to 3 and you move the bond from the double to the single bond. Okay, you exchange the single with the double and you move the charge from 1 to 3. This is how the resonance takes place. Now you have the positive charge on this carbon, which will attack the remaining halogen. It will be attacked by the remaining halogen, giving the 1,4 addition. And the double bond has moved to the center of the structure. This is the 1,4 addition. So when do we get a 1,2 addition and when do we get a 1,4 addition? If you are when do we get the 1,2 addition and when do we get the 1,4 addition? If you have your conjugated diene, and you add a hydrogen halide to it, you can have two conditions. You can either use the freezing conditions, where you use temperatures below 80 degrees, below zero, you go to negative or minus 80 degrees centigrades, or you use room temperature, where you use 40 degrees centigrades. When you perform this reaction at freezing conditions at negative 80, you get the 1,2 addition. Why do we get the 1,2 addition? We get the 1,2 addition because you have frozen your compound, which means that you did not allow it to do any of its processes. You did not allow the resonance. You froze the compound. As we always say, when your mother wants to extend the expiry of a product, to decrease or to stop or to prevent microbial attack on the compound and prevent regular or normal deterioration processes of the compound, she freezes the compound. She puts it in the freezer. In this case, you have stopped all natural processes. Resonance is a natural process, so when you freeze the compound, you stop the resonance, so you get the regular 1,2 addition. However, if you run this reaction at room temperature, you will not stop the resonance, so the resonance will take place and you will end up with the 1,4 addition product. So freezing stops the resonance and gives the 1,2, while room temperature allows the resonance and gives the 1,4 addition. To further explain the stability of compounds, we have to mention, this is just something for your knowledge, you have to know that stability of the benzyl carbocation is higher than the allyl carbocation, is higher than the tertiary carbocation, higher than the secondary, higher than the primary, and finally higher than the methyl carbocation. Why is that? In case of the benzyl, when your CH2 is carrying a positive charge, it is stabilized by 3 double bonds of the benzene ring, while in case of the allyl, it's stabilized by resonance by just 1 double bond. So you have here 3 resonating structures, you have here 1 resonance, and here you have the stabilization of the 3 methyls or the 3 carbons on the carbocation, 3 donating ability by induction, so you have 3 inductive effects. On the secondary you have only 2 carbons, so you have 2 inductive effects. On the primary you have only 1 carbon attached to your carbocation, so you have only 1 induction reaction. In case of methyl, you do not have an inductive effect whatsoever. This is regarding the regular addition reaction that can be performed on conjugated dienes. We said that we have another addition reaction, which is the cycloaddition reaction, which we call the Diels-Alder reaction. In the Diels-Alder reaction, you have the diene, this is your diene, and you have what we call dienophile. Dienophile, something that loves the diene. Phile means loves, so it's something that loves the diene. What happens is that the double bond accumulates its electrons on one of the carbons of the dienophile. So this carbon now is carrying a negative charge. It attacks the diene, removing the double bond to this central bond, again opening this bond, putting a negative charge here, which will attack the positive charge. The final product is like that. You have already this. These are the 4 carbons of your diene. Now you have just bonded them to your dienophile, so you have a bond here and a bond there, and you have moved the double bond to this carbon. What you did is you bonded this carbon with that one, you bonded this carbon with that one, you removed the double bond from the dienophile, and you moved the double bonds of the diene to the central bond, like that. This is your Diels-Alder reaction. In case to facilitate such a reaction, you can add an electron withdrawing group to your dienophile. If you have an electron withdrawing group, it facilitates the accumulation of electrons on this carbon because it attracts electrons towards itself, so the carbon attached to them will attract the electrons of the double bond towards itself, facilitating such a reaction. So whenever you have an electron withdrawing group on your dienophile, this facilitates such a reaction. We have examples of dienophiles. You need always a double bond that is attached to an electron withdrawing group. So if you add carbonyls here, carbonyls are electron withdrawing groups. This is maleic anhydride. You have to memorize these names, because if I ask for such a reaction using the names of the starting materials, you will have to recognize the name of the compound and to know that this is a dienophile. Again, you have the benzoquinone, you have the cyano compound. This is known as acrylonitrile. This is a cyano compound. You have the esters. In all cases, this is your dienophile. This part is your dienophile, and the rest of the structure is just the electron withdrawing group attached to this dienophile to facilitate the reaction. Let's look at the product. In each case, you will draw a ring, placing a double bond here, and you will remove this double bond. So you will draw a second ring and remove this double bond. And you will remove this double bond again, and you will remove this double bond. These are your products. This way we have finished discussing the reactions of the conjugated dienes. Let's look at them on the organized slides. As we have mentioned, they are addition reactions, either regular addition reactions or cycloaddition. The regular addition reactions can be a 1,2 or a 1,4 addition reaction. The 1,2 takes place at freezing conditions, -80 degrees centigrade, to stop the resonance from taking place, leaving the double bond in its place and just adding to one double bond of the 2 double bonds that we have. In case if we use regular temperatures like room temperature or higher, we will end up with the 1,4 addition, where each atom is added to one terminal of the conjugated diene. As we have said, the 1,4 addition takes place when the double bond, the first double bond, breaks, attacking the hydrogen, placing a positive charge on the central carbon, resulting into or attracting the resonance from the second double bond, giving the 1,4 addition, where it will place the positive charge on the carbon number 4, which will attack the halogen and give the 1,4 addition. As we have mentioned, this is the order of stability of carbocations. Finally, we have the Diels-Alder, which is a cycloaddition producing a cyclic ring, where the dienophile attacks the diene, moving the double bond to the central position, attacking another, provoking the second double bond to be opened and attacking the second atom of the dienophile, producing the ring. As we have said, this reaction is promoted by presence of an electron withdrawing group on the dienophile. Again, this is a second example where we have the diene and we have the dienophile, and again you will have an attack, breaking of the double bond or moving of the double bond to the central position, a second attack, and you end up with the ring. As we have mentioned, it's preferable to place electron withdrawing groups on the dienophile to facilitate such a reaction. Your dienophile has to have at least one double bond. Examples are the acrylonitrile, as we have mentioned, the acetylene, the ethylene, the benzoquinone, the maleic anhydride, any compound that contains a double bond and the double bonded compound is attached to an electron withdrawing group. This is an acceptable or suitable dienophile, and then you have your diene. But you have to notice that always in such conditions, the diene is in the cis, is in the S-cis for conformation. It has to be in the S-cis. If it's in the S-trans, it will not perform this reaction. So what happens is that you have a an equilibrium between the S-cis and the S-trans, because these are conformers, so they are interconvertible. Both of them are present. When you perform the Diels-Alder, what happens is that the dienophile will start attacking the S-cis, reacting with it, eliminating it from the reaction, forcing the equilibrium to be producing or synthesizing more of the S-cis. This is what is known as Le Chatelier rule, where it is known that when you have equilibrium between two moieties and you decrease one of the moieties, the equilibrium will be shifted towards forming the molecule that is being eliminated from the equilibrium. So this way, the little amount of the S-cis compound or the S-cis conformer will be eliminated, forcing the equilibrium to move towards forming more S-cis conformers, producing the reaction until there are no more S-trans and they are all S-cis compound or conformers, and the reaction moves towards completion. This way, we have finished discussing the dienophiles. I hope you have benefited from this video. If you have any questions, you can just post them on the chat and I will answer them as soon as I see them. Have a good day and goodbye in the next video.